This has been a really wonderful conference so far. I'm really grateful to the organizers for the invitation to speak. And it's been great to visit IAS for the first time, where the chalk is excellent. So I am going to talk about components of Springer fibers equal to Richardson varieties, and several of the talks the last few days have set me up very well. So this is based on joint work with Steven Karp. So there's a local expert. Where is Steven? Oh, there he is. He's sitting in the back row now. And so the goods and bads of having a local expert is, one, you could send him your talk notes to print them for you, but then he might respond with a list of notation he doesn't like. So, but luckily, so I will use notation that he approves. All right, so I want to talk about the components of Springer fibers, and nobody has said the word. I don't think we've talked about Springer fibers much so far, so I am going to start by defining them. So I will start with, so let's let lambda be a partition of n positive integer, and let's also take n, capital N, to be a nilpotent matrix. Of Jordan type lambda. So let me give you a quick example. So the maximum number size of matrix that I can write on the board is 4 by 4. And so if lambda is 2, 2, I will take a nilpotent matrix of Jordan type 2, 2. What does this mean here? I have 2 Jordan blocks, each of size 2. So I would like N to be the matrix that looks like this. Right, and so I can see my blocks here as each Jordan block, each has size 2. And since I fixed a partition, if I took a something like 3, 1, where the blocks are not the same size, I'm just going to make sure that the biggest block is first and then the smaller block. And actually, I do want to fix nilpotent matrix of Jordan type lambda. I'm going to choose a basis, and I'm going to assume throughout this talk that N is fixing to be this Jordan canonical form. Okay. So we want to make sure that we're fixing this in Jordan canonical form for this entire time. Okay. So definition. The Springer fiber of N is the following. So I like to denote it with this fancy B symbol, and I put a subscript of N. And this will be a collection of all full flags in the flag variety. So I like to use script B to denote the flag variety. And we're going to talk about type A. So you can think of this as GLN mod or L subgroup of upper triangular matrices, like was presented in Melissa's talk. She set me up very nicely. But now I'm going to put the requirement that my nilpotent matrix maps the ith subspace into the I minus first subspace. For all. So you can think of this as the flags that are fixed by my nilpotent operator. Right. And there's a lot of different ways of thinking about the Springer fiber. So I want to sort of remind you, okay, you might be asking yourself, why is this a fiber? So there's another way to think about Springer fibers is as fibers of what's called the Springer resolution. So this is the map that goes from the mixed space G cross upper V of U, projects down onto the nilpotent cone. And if you tease out these definitions, the fiber over a nilpotent matrix down here is going to be isomorphic to the flags fixed by that nilpotent matrix. So this is one of the reasons it's called, this is the reason it's called a fiber. Actually, another one that I wanted to mention because Melissa said the words Lustig variety is that another realization of a Springer fiber is a special example of a Lustig variety. So I'll use the same notation that she did. I'll use H here. So if you did the Lustig variety, and remember, you could put any element of the vowel group you wanted to here. So why not take the identity? Okay. And so, unlike in her talk, she wanted to put a regular semi-simple matrix here, but I will put a unipotent matrix, so I'll take the identity matrix plus n. And if you tease out her definitions of what the Lustig variety is with those two pieces of input, you will arrive at your Springer fiber. So these are two ways you might see these things in the literature. Are there any questions so far? This audience will know how to stop me with their questions. All right, so properties. Why do I like Springer fibers and why do I think we should all like Springer fibers? Let me tell you about many algebraic and combinatorial properties about Springer fibers. Okay, so starting with the following fact. So Spallenstein proved, and there's also a paper by Vargas that explains this as well. And you can find it in other places as well now that, one issue you might have is, these things are in fact not irreducible, they're reducible. So some people will take issue with me calling this a variety, but I'm gonna be okay with that for now. And so if it's not irreducible, what are the irreducible components? Well, the key fact here is, for this talk, the key fact is that irreducible components of Springer fibers are in bijection with standard Young tableau. So the key thing is, well, first, these things are equidimensional. Dimensional of dimension equal to, so what is the dimension? Well, you take I minus 1 and you multiply it by the ith part of your partition. That's a very nice number that we've probably seen in Combinatorics. And components are indexed by standard. So I would like to explain a little bit about how this goes. So let's write this down. So how does this work? Well, let me define a map for you that goes from the Springer fiber and it inputs any flag in the Springer fiber and outputs a standard tableau. Okay. So I will take a flag in my Springer fiber and I will associate this to a standard tableau in the following way. Well, this is entirely inductive. What I do is I will take this flag and send it to a standard tableau. So I have to tell you where to put n, and then I'm going to tell you to fill in the rest of this inductively. So let's see. I'm going to place n with the rule that V1 is in the image of n to the I minus 1. So let's say this is in the ith row. So this is row I. And the other rule is that V1 is not in the image of n to the. Is there a question? Yeah.
Are you going to say how to do the induction?
Yeah. Okay. Yeah. All right. And then if you give me your flag, what's a reasonable way to get a flag and a flag variety of one dimension smaller? Well, one reasonable way is to take every subspace in my flag and mod out by V1. Okay, so then this tableau will be the thing you get when you apply pi to the smaller flag where I mod out by V1.
but I need to like identify a basis of V mod or CN mod.
Yeah. Okay, wait, so, sure. So I look at my specific flag, the flag determines a basis. So I look at what V1 is, and I figure out what row N belongs to based on what V1 is. Then I mod out by V1. I look at what my nilpotent operator looks like on here. And this dictates the rest of the shape, and I do this by induction. Is that okay? Let's do a quick example. Here is a very straightforward example. So, here's a 3x3 nilpotent operator. Now lambda in this case is 2, 1. Let's see, I like to write flags as matrices, so let's take something like this. And here A is whatever your favorite complex number is. So you could stare at this matrix, and I claim that this matrix defines a flag in the Springer fiber. So what do I have to check? I have to check that N maps the ith column of this matrix into the span of the earlier columns. So first, this had better be in the kernel of N, and it is. And then, okay, I should see that the second column, when I apply N, gets mapped into the span of the first column, which it does, and so on and so forth. And then I know that I would like to assign this thing a tableau of shape 2, 1. Well, okay. When I stare at this guy, one way for me to think about this is mod out by E1. Mod your vector space by E1. And then think about the Jordan type of the nilpotent operator as it acts on the rest of your vector space. If I mod out by E1, I have essentially, what do I have left? Well, I have something E2, E3. Now that's in the kernel after I mod out by E1. And E2 will also be in the kernel. So if I think about what's the span of this guy left over, I think about how N acts on this. Now it's 0. Okay. So 3 had to go here and 1, 2 goes here. Yeah.
Is there much reason to work with quotients instead of subs?
No. So it's up to like whatever conventions you would like. So if I understand your question correctly, you're pointing out to me there is another very reasonable choice here, which is that instead of quotienting by V1, you restrict N to Vn minus 1, and you do your induction that way.
Yeah.
That works perfectly well. Spallenstein set it up with quotients. And if you read carefully, like a paper of Steinberg, which I'm about to tell you about, he sets it up with like restricting to Vn minus 1. And those two conventions, they will exchange your tableau that you get out of the assignment by the dual, sigma and sigma dual. I'll say that in a second. Yeah.
I blanked for a minute, so this is a dumb question, but do you modify N when you go to do it on the quotient?
You just restrict N to this quotient, right? Because this is a Springer fiber, because I started with the flag in here, quotienting gives me a well-defined flag for the Springer fiber for N restricted to this thing, right? That's the way that.
Are you saying these components don't intersect?
I say what?
These components don't intersect each other?
No. They do intersect each other. So, okay, let me finish. Okay, let me finish the story here. So, let me at least say something about like what I will define these components to be. So let's see, so we will define the component corresponding to sigma is going to be defined in the following way. So I will write B sub sigma. So here sigma is my standard Young tableau of shape lambda. And my component that I'm going to take is I'm going to look at all the flags that were assigned to sigma. And if I let myself vary over all standard Young tableau, those would be disjoint, but then I want an irreducible component, so I'm going to close it up. And now there's definitely intersections. So these things are connected, right? but you have these different components indexed by standard tab. So that's this is one beautiful property of Springer fiber. So let me keep marching through my list of the way the combinatorics of standard tableau is closely related to the geometry of Springer fibers. So let me mention, okay, why are they called Springer fibers? So this is in the mid-70s, but then this has been proven many times over. Borho, McPherson, and also Lustig. Name should come up. So Springer fibers are key objects in geometric representation theory. So let me just tell you sort of one result that encodes this information. And well, I just explained to you that for each Springer fiber, there are standard tableau many irreducible components, and they're all the same dimension. So this tells you that the cohomology of this nice vector space, the top dimensional piece of your cohomology, has dimension equal to the number of standard tableau of shape lambda. And lots of folks in this room like the symmetric group. So what other vector spaces do you know have that dimension? Well, irreducible representations of the symmetric group. And so the key result is that this is an irreducible representation of this. Right, and it's going to be, well, depending on how you set this up, right, there are some conventions. It's either the representation indexed by lambda or representation indexed by lambda dual. Does this make sense? I don't know what's happening. So this cohomology fact, this is Springer's result, and I want to point out, like, I am talking about the sort of like type A Springer fibers. There are analogs of this result in all types. It's a very beautiful theory. And there was a lot of machinery around the derived category developed by Borho, McPherson, and Lustig to think about this, what's called the Springer correspondence in all types, which is sort of a correspondence between irreducible representations of, like, replace SM with the Bow group and representations on these top pieces of homology of the Springer. If you look at Maria Gillespie's blog, she calls this like a gemstone, and I heartily agree. This is a really beautiful theory. So a few other key facts. So this is the paper I mentioned just earlier when Alan asked this question. So Steinberg actually proved that if you apply Robinson-Stedchet to the pair of tableau here, you get out for this the unique permutation.
Their sigma was a tableau, right? And now it's a permutation.
What?
Up there, sigma was a tableau.
Yeah, tableau. No, it's still, this is still tableau. Yep, sigma and tau are still tableau. You get out the unique permutation. That's determined by the relative position. The relative position of generic flags, a generic flag from the component indexed by sigma and a generic flag from the component indexed by tau. Can you remind me what price? Robinson-Stedchet correspondence, right? Am I saying this? And what am I?
Since
I think normally it would be RS inverse, but yeah.
Yeah, that's.
Oh, that's why I'm getting confused looks.
Yeah.
Because I'm writing that like, okay.
And this means the intersection of the B sigma with the tau is the.
So you take a generic flag here and a generic flag here, and this uniquely determines some permutation that says the relative position of those two flags. And the permutation that you get out is what you should get when you feed this tableau to your algorithm. Thank you, yeah, I need it. Steven, why didn't you tell me that when you looked at my? So that's okay, okay, so like little asterisk, Steinberg's conventions, he likes a slightly different setup where you restrict your flag to the n-1 subspace. So you have to be careful with conventions here. And I always have to just do an example with my conventions to figure out. So you might have to put some duals in here to get exactly what I'm saying. So.
What does it mean though, the relative position of two flags?
So the way I think about it is you like think about, like the flag variety cross the flag variety. And the sort of the diagonal G orbits on that are indexed by permutations. So these two flags will lie in one of those orbits, and that uniquely determines your permutation.
Okay, thanks.
I think that's the right way, one way. And this also was like coming up in Melissa's talk, right? So one other, I think, cool result about these Springer fibers is if we let, let's say, phi from flag variety to flag variety be the isomorphism given by taking the dual flag. And, right, so if you give me a flag, I can give you another flag out, but I just take the dual of every subspace and I reorder them, right? The dual of a one-dimensional subspace is explicitly an n-1 dimensional subspace. And this map is going to take a Springer fiber to the Springer fiber of your matrix transpose, okay? And so Van Leeuwen actually proved that when you take the image of my component corresponding to sigma under this map, I get the component of the Springer fiber, but now I'm taking the dual here. Okay. So this is the evacuation tableau that we get. So Springer fibers, sort of their geometry is closely interconnected with all the different combinatorics of tableau that you can see.
Dual flags means no flags of quotients.
Where are we?
So when you say taking dual flag, that means I can take duals of vector spaces and I'm gonna get quotients. That's one way to do it.
That's right.
Okay.
And then reorder. Yeah, exactly.
Okay.
Which is also one of the reasons why I was saying that sort of the other natural thing to do here is restrict your flag to the n-1 subspace. And when you do that, Van Leeuwen's like theorem says, oh, you just get the involution of, or the evacuation of whatever tableau Spaltenstein's conventions. Steven and I call this like Spaltenstein versus Steinberg conventions. And we have our own preferences, so we have sometimes some issues. It's okay. All right, okay, this makes sense. So I wanted to hopefully convince you that these are interesting things from both a geometric and combinatorial perspective. So let me say something about open questions. So if you want to think about Springer fibers, it might seem, well, okay, I guess from what I've said, you sort of are aware that have already been thought about a lot in the literature. But let me tell you about questions that are still active areas of research. And one big overarching question is understand the geometry of the components. So, okay, maybe I'll compare this to Schubert varieties. If I ask you, okay, here's a permutation indexing a Schubert variety, what is its Poincare polynomial? Well, you're going to tell me I look at an interval, a Bruhat interval, I can write down the ranks, and I have an answer. If I say, is that Schubert variety singular? you can figure it out very, very quickly, right? You look for patterns in your permutation. So I don't know the answer to this question for arbitrary Springer fibers. You give me a standard tableau. What's the Poincare polynomial of that component? Is it singular? So basic things like Betti numbers and singularities are in general open, but to sort of follow Trisha's rules from yesterday, there's a lot of partial results in the literature that, like, there's people who have been thinking about this, and so most of the progress is in special cases. So if my partition has 2 rows or 2 columns or is a hook, then a lot of these questions are answered in really satisfying combinatorial ways, but there's no sort of overarching rule that we can give. So 2 rows, 2 columns, hooks, et cetera, et cetera. And I'll list a few names, work by people like Fressa, Melnikov, Hong. There's a lot that you can find there. So another problem or another question that we can find in the literature that I don't think is fully solved. I know it's not fully solved, or I can't find the answer. There's a problem that was posed by Springer in the 80s. And that is the question of, well, what is the class? What's the cohomology class of this thing? And all right, if I would like to expand it using a Schubert basis, what are these coefficients? Right, these things should be integers, and I would like to know how to compute that, right? So I have a standard tableau, a very combinatorial object. Can I find some statistics, some information that tells me what these numbers should be? So I have found 2 papers that answer this question, and if anyone knows of other ones, I'd be thrilled to hear about it. Or not entirely, but in special cases, right? So let me tell you about 2 sort of special case on my speaker board. So 2 special cases where there is an answer to this. One is a paper of Jones. Actually, don't know if I'm pronouncing his name correctly. Let's find it. So 2 special cases. One is the case of all hooks. Hooks is one case where we know almost everything you might want to know about components of Springer fibers. And in this case, there is a combinatorial formula that answers this problem for Springer fibers. That's in work of Yost. There's a combinatorial formula. And in particular, this formula enumerates certain tableaux and uses the information of the tableau to get a permutation. So it gives you a way of generating the answer. And then the other case where I have seen work on this is for special components of Springer fibers. Related to K orbits. And here the result is due to Bill Graham and Roger Zero. The local expert. And so this is another situation where I'm not going to go into much detail, but the special component is they look at some K orbits and then they have a way of associating to some K orbits components of Springer fibers. And unlike this case, they're not fixing a partition shape. they're coming up with components of all different kinds of partition shapes, and then showing for that special class that they can actually give an answer to this problem. I think that there's like a K-theoretic, in fact, an equivariant cohomology answer, which then specializes to the sort of ordinary class. Okay. Lingering questions. And we'll ask Bill to give a mini talk about that later so that I can understand. Okay. All right, so, oh my goodness, this is going by really fast. Why are Steven and I studying these things? So now let me tell you about our hook into this. Oh. So I went to go visit Notre Dame maybe like 2 years ago, gave a talk in a seminar. I went to grad school there, so every once in a while they agree to have me back. And when I was there, I don't know if I met him for the first time. I met this postdoc named Steven Karp. We talked a little bit. I was like, okay, come visit WashU. He agreed. So he came to give a seminar at WashU. And then we spent like a very happy afternoon where we were talking about like, well, what should total positivity mean for like certain subvarieties of the flag variety? A lot of folks in here might know, I think a lot about Hessenberg varieties. So I was like, let's think about totally positive Hessenberg variety. We proceeded to do a bunch of examples. I speculated wildly, and then he told me why my speculations were false in most cases. But okay, after that, we decided to keep talking about this. So we decided to start a little learning project because there was an archive preprint called Total Positivity in Springer Fibers that was written by Lustig. So you can find this on the archive. And so Lustig considers like something he calls a totally positive Springer fiber. So let me remind you what that is. So if I want to define a totally positive Springer fiber, what am I going to do? Well, I am going to take my totally positive flag variety. I'm going to intersect it with a Springer fiber, and that's what I will call my. So this definition is I take my Springer fiber and I intersect it with this.
I mean, you do a sub n versus a sub sigma.
Say that again, what?
I mean, what's the difference between sub n versus?
This is the whole Springer fiber,
That would
and
be
sub
that.
sigma was the component of the Springer fiber. So this is a union overall standard tableau shape lambda of the components. And then this would be the whole Springer fiber. Good. So I am not a totally positive person. From a different perspective, like Melissa was like, oh, I do this, and this is why you really care about open Richardsons. But one of the things I've learned as part of this project is that, okay, if you want to think about the flag variety, here, this totally positive flag variety, how should you break it down? Well, you should use open Richardsons, right? Like totally positive part of open Richardson varieties. So there's a natural decomposition of this totally positive flag variety that's indexed over V less than or equal to W of these open Richardson varieties, but I'm going to look at their totally positive. So here, this is the open Richardson variety that was like in Melissa's talk, but now I'm intersecting it with my totally positive flag variety. So here's an incredible theorem, or I think is a rather incredible theorem due to Lustig, which I found incredibly surprising. So this paper had been on the archive for a while. We started reading it, and here's the main result, which I'm going to phrase in our notation. There's something much more general in this paper. So if you want to study the totally positive Springer fiber, then Lustig tells you that actually you have to take a subset of these cells. And there's a subset of these cells that actually give you this totally positive Springer fiber, which should be very surprising because actually like that is not, like the Springer fibers are not well behaved in that way, right? It's not like, oh, there's some Bruja cells that like sort of pave Springer fibers, that's not the case. That's one of the reasons why like these Betty number questions are still open. So there exists a subset, so I'll have to tell you what that is. So we get a special union of these cells where the union is over. So two things. Well, one, so first of all, I guess, well, V has to be less than or equal to W, such that I am going to require that V and W are both shortest, this is like shortest right coset representatives. So lambda gives me a Young subgroup, and I'm going to pick the permutations that are shortest left coset representatives with respect to that Young subgroup. I'll show you an example in a second. So that's not such a surprising restriction, actually. But then two, I will take all the pairs with the property that when I multiply SI by V, I get something that is not less than in Bruhat order to W. And this is true for all simple reflections that are indexed by I, which is in the set of N minus lambda 1 plus lambda 2, etc. So this would be the set of simple reflections that actually generate that Young subgroup corresponding to the partition length. So it's a very sort of simple Bruhat order condition that dictates exactly what of these cells lie in the Springer fiber. And it's fully non-negative Springer. Any questions like that? That makes rough sense, okay? All right. So then Steve and I read this, we did a bunch of examples. As part of writing this talk, I went back through some of our old talk notes. We kind of like tried different cases, thought a little bit about it. So there's some really basic questions you could ask. Well, one basic question is like, are totally non-negative Springer fibers the same dimension as Springer fibers, right? Or maybe when you intersect, the cells all drop, and so you don't, keep the same dimension. So we did a bunch of examples. It seemed like we could always find a cell that was this maximal dimension. And then at some point, Steven made a really nice observation, which is the following. So we started focusing on like, okay, well, when are these cells that we're getting the maximum dimension? And we had the following observation that we get this I and B and greater than 0 has maximum dimension. So I was also interested in when is it that this thing has exactly the same dimension as the original Springer fiber. So that dimension was the sum over I minus 1 lambda I. If and only if, well, if this has maximum dimension, I'll take the Zariski closure and I'll get something that's a subvariety of my usual Springer fiber sitting back in my complex flag variety. So that means that my Richardson variety corresponding to U and V is a component of my Springer. Okay, so then my X U intersect X V opposite, okay, is a component of the Springer fiber, now back in my usual complex setting Bn.
So are you taking the positive part of the Richardson as risky dense in the Richardson?
Yes. Ask the local expert about that. And my impression is that that's not necessarily hard. And in fact, like this observation would follow if you look carefully, you're just trying to figure this out. And we realized like, okay. So then I said, aha, well, surely this is in the literature. Somebody has characterized in type A, because we have combinatorics of standard tableau, which components of Springer fibers are just like, which one is equal to a Richardson variety. I couldn't find it, so I'm going to tell you how to do it. If somebody has seen things like this already in the literature, please let me know. I would love to see how somebody else attacks this. All right, so let me get to the results and tell you a little bit about the combinatorics that we found that's motivated by this geometry. But I guess one answer is that Lustig told me what to do already, actually. So he has already answered this question in the sense that he told me it's pairs V less or equal to W that are both shortest right coset representatives satisfy the condition, and so that the difference in their lengths is equal to that statistic. So I do have an answer already, I guess, in the literature, but because components of Springer fibers are indexed by tableau, the natural question is like, well, what's the subset of tableau that correspond to this property? So here we go. I have not seen these tableaux before, so again, we'd be interested if anyone has seen the kind of tableau that we ended up looking at. Okay, so let me tell you what to do. So you give me a standard tableau of shape lambda. Let me give you two permutations. Okay, so I'm nervous because we're gonna do weird reading words again. So I'm gonna let W sigma be the unique permutation with the property that W naught W sigma inverse be the I'll just say top down reverse reading word of sigma, which I guess a lot of people just say the reverse reading word. So I'm reading from the top row to the bottom row and from right to left. I'll do an example of just a second in just a second. And I'm gonna let V sigma inverse be the top down reading word of not sigma, but the image of sigma under evacuation. Let me show you a quick example. So here's sigma 1, 3, 4, 6, 2, 7, 5, 8. Here's the evacuation. And okay, I'm just gonna skip right to, well, okay, maybe I'll do this. So if I write down, so what is W naught W sigma inverse? Reverse reading word of sigma. So 6, 4, 3, 1, 7, 2, 8, 5. And then V sigma inverse is 1, 4, 6, 7, 2, 5, 3. Or I like the English reading word of your tableau. But I know that reading word means from the bottom up, left to right, usually, right? So I just learned. So let me tell you the theorem. So theorem. So the component of the Springer fiber indexed by the standard tableau sigma is equal to the Richardson variety. Oops, X. So intersection of Schubert for W sigma, opposite Schubert for V sigma, where permutations are defined like that. If and only if for all J in N. The last entry of sigma, let me write it as J minus 1. This is going to mean you restrict your tableau to the entries 1 through J minus 1. There's a sub tableau I get in that way. So I want that the last entry of this tableau in the row above J in the row above J is larger than every entry in the rows below.
You had passed to the totally positive situation. Is there something totally positive in this theorem or? am I
No.
missing?
So
Okay,
I've sort of used this observation and now I'm just asking like, okay, Lustig has told me sort of a way to like find data, like what of these cells have max dimension in my totally positive Springer fiber. And now I'm closing things up using this risky closure and saying, okay, that would mean that my component, if it is actually a Richardson variety. Yes.
Does this characterize all top degree components or only certain ones?
Oh,
So every B sigma of top degree looks like a
looks like
Richardson.
this. Yes. So you might want to, okay. All right. Yeah, like there's an equality here. So I picked a basis at the beginning. I said n is an Jordan canonical form.
Yep.
So like for this n, this is going to tell you when these things are equal.
Okay.
And these are the only ones that are Richardson, right?
Mhm.
We are actually able to show that if it's not true, then you have a strict subset. It turns out this is always a subset of this thing. But if sigma does not satisfy these properties, okay, then the dimension of this guy is too big. And you can argue that this is the sort of smallest Richardson that contains the components, so it would, if it was equal, it has to be this.
Can you repeat what your notation means, 2 sigma of J minus 1?
Yeah, restrict sigma to the entries of 1 through J. Like restrict to 1 through J, or 1 through J minus 1. I don't know, is there like is there a known notation for that in the literature? I mean, I guess then we made one up. Like a restriction sign? Okay, I should. Okay. So, okay, look up there. Okay, let me quick go back thing and cover up my theorem. So let's look at this. So starting with the biggest number, 8, I ignore it. I look at the entry in the row above us, 7. Is it bigger than everything in the row below? That's 5, yes. Do the same thing with 7. Above I see 6. Is 6 bigger than 2 or 5? Yes. Okay, I keep going with that. So this is an example of a tableau that meets my requirements.
So when you're in the top row, then
It's vacuous.
Okay.
Yeah, there's nothing in the top row. So let me give you a non-example. Okay, a non-example is this guy. Okay. So specifically, if you were to focus on 6, so I ignore everything bigger than or equal to 6. So 4 is appearing above that one. Is 4 bigger than both 3 and 5? No, it is not. So this is a non-example of that condition. So I've never seen a condition like this one before. So we would decide to name the set of I don't, we were like, what should we call this? So I guess for now, we're calling them Richardson tableau. But sometimes I think things should be named for the properties they have, so there may be good reason to call them something else. I've never seen these tableaux in literature. We'll call them Richardson tableau. Oh. All right, so I have about 10 minutes. I want to tell you a little more about these tableaux. Before I do that, are there questions still?
I was just gonna ask, is there a next enumeration of Richardson?
It's coming, yes. Yeah. Okay, so let's talk about these Richardson tableau. Let me, one quick corollary. So let's see. Okay, let me list a few more examples. Because when you start doing these things, it's nice to know like what kind of things have this property, what kind of things do not. So if you're a 2-row tableau, which remember I said Springer fibers, there's a lot of results about 2-row situation. Then, the condition of being Richardson. You're Richardson, if and only if you have no consecutive entries in row 2. So you can think about that for a little bit. As Zach pointed out, the top row, like, so like if you look about entries in the top row, this condition is vacuous. And because of that, all hooks are automatically going to satisfy this property. But on the other hand, you can convince yourself that if you had a rectangle shape, there's a unique one. There's just one. And it's going to be the one that looks like 1, 2, 3, say like 4, 5, 6, 7, 8. That's the only thing that you can see.
It's a transpose.
Oh, sorry. Thank you. Otherwise I will get him. Yeah, okay.
Yeah.
Thank you.
The 2-row.
I got carried away.
That's the maximum match.
Okay, so that is a unique one. So it's an interesting observation. So actually another corollary from this theorem, that because of time let me not write down, is that we can always find a Richardson tableau of any shape, which means that we can always find we have a component that's always a Richardson variety. I actually think that something like that was already known in the literature. So that would imply that the totally non-negative Springer fiber has the same dimension as Springer fiber. There's at least one cell in there that has the max dimension. But now we kind of have a way to enumerate exactly how many of those cells have the max dimension. So let's talk about properties of these tableaux. So here is one property of these Richardson tableau. And it is that sigma is Richardson if and only if, when you're computing evacuation, now you do all these slides, the only kind of slide you're allowed to have is an L slide. You go down and then over. And because I cannot compute evacuation on the fly. Okay, so here's my example, and here's my non-example from earlier. So I'm showing you my process of sliding, which we can learn about from Professor Fulton's book, right? And as I slide, I recognize that this Richardson one, okay, like there's some along the top row, but every slide is go down and then over. Well, this one was just across the first row, but down and then over. Whereas this non-Richardson one that I gave you, eventually I have a slide where if I follow this trail I get, I actually have to go over and then down, right? So I have like, anytime you have a sort of zigzag slide, you're not this Richardson tableau. So the set is closed under evacuation. Which was this dual operator. And okay, given the fact that we had Van Leeuwen's like results, that there was this isomorphism from flag variety to the sort of dual flags that should send component to this should not be surprising. Like if we follow that through, we should see that sort of the Richardson varieties on one side, you sort of flip things around, you get another component that must be Richardson. And then finally, let's enumerate them, okay? I think something that was like very surprising is that this formula exists. Wait, okay. At first, this seems a bit shocking, but the number of these tableaux of shape lambda is equal to the following product of binomial coefficients. So lambda L minus 1, choose lambda L. Lambda L minus 2 plus lambda L, choose lambda L minus 1 plus lambda L. Then we do lambda L minus 3. Choose L minus 2 plus lambda L minus 1 plus lambda L.
It's sorted in an increasing order.
Yes, lambda is lambda 1 greater or equal to lambda 2, etc. And so what you're doing is you're doing like partial sums, but you're like tweaking what you take at the end. This is like, yeah, we get sort of a smaller thing on the bottom by, taking the later element. And then the last term here would be lambda 1 plus lambda 3. Choose lambda 2. I have like 2 minutes, but it's almost lunchtime. So let me say one more corollary, which, okay. If we're Richardson, then suddenly this class is a product of Schubert's. Okay, so maybe there's a reason it's hard to read off exactly what things show up in the sum. But we would get then something we could compute as the product of certain Schubert varieties. It did my conventions correct. Maybe a remark about this thing is generating functions proof. So I do not know a sort of bijective enumerative kind of proof of this thing. And okay, let me end. Oh no, well, let's do this. This one, no, it doesn't not have to get, I did the wrong last board, but let me end with this example, because if you remember, I said in the literature, there is this formula due to Güemes that gives a combinatorial formula for the hook case. Well, our proof says every hook has components that are Richardson varieties. So that means that this existing formula is going to tell us how to write down the product of these Schubert polynomials. So I guess, okay, this product is very hard, right? You could create a career out of studying this product, I think. But there's maybe some hope here, right? Like somebody has done this in the hook case and found an enumerative formula, which I could explain if people are interested after the fact. I don't want to take a lunchtime. But yeah, there's like a clear sort of next question, which is like, we could now do this for hooks. Could we answer the question for this product where sigma is another one of these quote unquote Richardson tableaux? Okay, so thank you so much for your attention. Larry, yeah.
So that product will be multiplicity proof?
I don't know. No, this example I did, it happens to be. You mean like, are there any coefficients here that are like
Well,
two
'cause
or?
in the Güemes formula, do you know if it's multiplicity proof?
No, I don't know.
Okay.
I don't know. But so here there's some things like staircase shaped, what he calls reduced tableau. And the thing that comes into play here is the numbers across the top have to match the positions of certain 1, 2, 3 in here. So I'm happy to talk more about it, but yeah, it's not obvious to me that that his formula gives you something that's multiplicity.
Cool.
Yes.
So this form, your corollary tells you the dimension of B segment, right?
Our corollary tells you the dimension of, say that again?
B segment, because, I mean, it's the full dimension on the right hand side would be the degree. So
Sorry, I lost something. Translation. The dimension of
the degree of the right hand side.
the degree of this side.
Co-dimension of the variety, right?
That's right.
You know what that is. So we've
Yes.
added up all of your Richardson tableau, Q to the dimension of the corresponding variety.
Okay,
Did you look at that generating function?
no, I don't think so. No. Okay. So wait, your suggestion is to add a Q to some property, look at that generating function, see what it looks like. Okay, thank you. That's a great suggestion. Other questions?
Is your rectangular tableau self-evacuating?
Yes,
Is there something special about self-evacuating Richardson tableau?
I don't know. Yeah,
In the world of finger fiber components, how rare are they?
well, rare, like if you compare this number to the number of total standard tableau of shape lambda,
Yeah,
at least for this fixed basis. So I guess this would be relatively rare.
do you know a percentage?
No, no, no.
Okay.
There's a lot more standard tableau than this. Ton. Relatively rare. Yeah,
Is there anything special about these vectors in the SN rep?
anything special to say that about the,
You've identified some vectors in the SN rep corresponds to the Springer fiber.
sorry, I identified, say that again, some vectors and the,
So the Springer fiber is identified, homology of the whole Springer fiber
Right.
is an SN representation.
that's right.
You're telling us you found some special vectors,
Okay, yes.
but
Oh, you're saying like from a representation theory perspective, like what should this be? I don't know the answer to that question. I don't either. I guess the thing is though, that I would sort of expect that like the Springer representation should mix these all up with the other ones too. So I don't know if there's some special meaning of these. There's an interesting combinatorial thing by Pagnon and Russeret. They study a like partial order on standard tableau. And they say some things about the geometry of components of Springer fibers with respect to that partial order. And I think this probably won't answer your question, but like my intuition is maybe that perhaps in that sort of partial ordering there, this subset is sort of nice. And then maybe if you kind of study moving away from the subset, you might be able to say something about things that are not sort of Richardson. I don't know. Yeah. Last questions?
Let's take more.